Right now, as you listen to these words, light is traveling from your screen to your eyes at 299,792,458 meters per second. The electrical signals in your brain, the ones allowing you to comprehend this sentence, move much slower, but they're still governed by the same fundamental limit, the speed of light. It's not just a number in physics textbooks. It's woven into your existence, into every atom in your body, into every force that holds those atoms together, into every moment of your perception. And here's what makes it profound. Nothing can go faster, not particles in the most powerful accelerators, not signals between distant stars, not even gravity itself. This isn't a challenge waiting to be overcome. It's a fundamental truth about reality. Tonight, we'll understand why. Settle in, and let's explore the cosmic speed limit together. This is Sleepy Time Universe. A peaceful journey through space, science, and cosmic scale, designed for relaxation. Get comfortable, let your breathing slow, and let's begin this journey into the deepest structure of our universe. Part 1. The discovery of a limit. The long history of measuring light. For most of human history, light seemed instant. You opened your eyes, and the world appeared. No delay, no travel time. Ancient philosophers debated whether light was emitted from the eye or received by it, but few questioned whether it moved at all. The first serious attempt to measure light speed came from Galileo in the 1600s. He stationed assistants on distant hilltops with covered lanterns. One would uncover their lantern, and when the other saw the flash, they would uncover theirs. Galileo would try to measure the delay. It didn't work. Light was simply too fast for this method. The delays Galileo measured were entirely human reaction time. But the attempt was important. It established that the question could be asked. The breakthrough came in 1676 from an unexpected source. Ole Rømer, a Danish astronomer, was studying Jupiter's moon Io. This moon disappears behind Jupiter once every orbit, like clockwork. Rømer noticed something peculiar. When Earth was moving toward Jupiter in its orbit, Io's eclipses happened slightly earlier than predicted. When Earth moved away from Jupiter, the eclipses happened slightly later. The pattern was clear. Light took time to travel. When Earth was closer to Jupiter, the light had less distance to cover. When Earth was farther away, the light took longer to arrive. From these observations, Rømer calculated that light traveled at about 220,000 kilometers per second. Not perfect, but remarkably close to the true value for such an early measurement. This was revolutionary. Light had a speed. It wasn't infinite. It wasn't instantaneous. It was fast, incomprehensibly fast by human standards, but it was finite. Refining the measurement. Over the next 2 centuries, scientists developed increasingly clever methods to measure light speed more precisely. In 1849, French physicist Hippolyte Fizeau used a rapidly spinning tooth wheel. He shone light through the gaps between the teeth, bounced it off a distant mirror, and measured how fast the wheel had to spin for the returning light to pass through the next gap. His measurement, 315,000 kilometers per second. Léon Foucault improved on this method using rotating mirrors instead of toothed wheels. He measured 298,000 kilometers per second. Getting closer. By the late 1800s, Albert Michelson had refined the technique to extraordinary precision. He built an apparatus that bounced light back and forth between mirrors on mountaintops. His measurements approached 299,792 kilometers per second, accurate to within a fraction of a percent. These increasingly precise measurements served a purpose beyond mere accuracy. They revealed something profound about light. No matter how you measured it, no matter what direction you pointed your apparatus, no matter how Earth was moving through space, light always traveled at the same speed. This constancy would soon reveal that our understanding of space and time itself was fundamentally wrong. The Michelson-Morley experiment. In 1887, Michelson teamed up with Edward Morley for an experiment that would shake the foundations of physics. They wanted to detect Earth's motion through something called the luminiferous ether, a hypothetical substance that supposedly filled all of space and carried light waves, much like air carries sound waves. The logic seemed sound. Earth orbits the Sun at about 30 kilometers per second. If light travels through a stationary ether, then light moving in the direction of Earth's motion should appear slightly faster, and light moving against Earth's motion should appear slightly slower. Just like sound travels faster downwind than upwind. They built an interferometer, an exquisitely sensitive device that could detect tiny differences in light speed by comparing beams traveling in perpendicular directions. They expected to measure variations as Earth moved through the ether at different angles during its orbit. The result shocked everyone. No variation. No matter which direction they measured, no matter what time of year, light traveled at exactly the same speed. The effect they expected to see simply wasn't there. At first, physicists tried to explain this away. Maybe Earth dragged the ether along with it. But that created other contradictions. Maybe objects contracted in the direction of motion through the ether, perfectly compensating for the speed variations. George Fitzgerald and Hendrik Lorentz independently proposed this idea, deriving equations for exactly how much contraction would be needed. They were close to the truth, but they were still thinking in terms of objects moving through a fixed space. The real answer was far stranger. Space itself was not fixed, time was not absolute, and the speed of light was woven into the fabric of reality in a way no one had imagined. Part 2. Einstein's Revolution. Special relativity emerges. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that would change physics forever. Albert Einstein had been thinking deeply about light, motion, and the puzzling results of the Michelson-Morley experiment. Einstein made a bold move. Instead of trying to explain why the experiment failed to detect Earth's motion through the ether, he proposed that the ether didn't exist at all. Light didn't need a medium to travel through. It simply moved through empty space at a constant speed. More radically, he proposed that this speed was the same for all observers, regardless of their motion. Think about what this means. Imagine you're on a train moving at 100 kilometers per hour, and you shine a flashlight forward. Common sense says that someone standing beside the tracks should see the light moving faster. The speed of light plus the speed of the train. But Einstein said no. The person beside the tracks measures the light traveling at exactly the speed of light. not light speed plus the train speed, just light speed. This seems impossible. How can two observers in relative motion both measure light traveling at the same speed? The answer forced Einstein to abandon assumptions about space and time that seemed obviously true. If the speed of light is constant for all observers, then space and time themselves must be flexible. They must stretch and compress in precisely the right ways to ensure that everyone, regardless of their motion, measures light traveling at the same speed. This was special relativity. And from these simple principles, Einstein derived consequences that seemed to violate common sense. Time dilation. If you travel at high speed, time slows down for you relative to someone who remains stationary. This isn't an illusion or a trick of measurement. Time actually passes more slowly for you. Imagine two twins. One stays on Earth. The other boards a spacecraft and travels at 90% the speed of light to a distant star and back. When they reunite, the traveling twin has aged less than the twin who stayed home. If the journey took 10 years, according to Earth clocks, only about 4.4 years passed for the traveling twin. This has been measured countless times. Put an atomic clock on an airplane, fly it around the world, and when it lands, it reads slightly less time than an identical clock that stayed on the ground. The difference is tiny, nanoseconds, but it's real and measurable. GPS satellites experience time dilation. They orbit at high speeds and experience weaker gravity than we do on the surface. Both effects cause their clocks to run at different rates than Earth. Clocks, without corrections for these relativistic effects, GPS would accumulate errors of about 10 kilometers per day. The fact that GPS works is daily proof that time dilation is real. Length contraction. Objects moving at high speed contract in the direction of their motion. A spacecraft traveling at 90%, the speed of light would be compressed to less than half its resting length from the perspective of someone watching it pass. The people inside the spacecraft wouldn't notice. To them, their ship looks normal, but they would see the space between their starting point and destination contracted. What Earth observers measure as 10 light-years of distance, they might measure as only 4.4 light-years. This explains something puzzling. Cosmic ray particles created in Earth's upper atmosphere travel at speeds close to light speed. At these speeds, the particles decay so quickly that they shouldn't reach the ground before disintegrating. Yet, we detect them at sea level. The answer is length contraction. From the particle's reference frame, the atmosphere is compressed to a fraction of its normal thickness. The particle doesn't need as much time to traverse it before decaying. Mass and energy. Einstein's most famous equation, E=mc2, reveals a deep connection between mass and energy. They're not separate things, but different aspects of the same underlying reality. This equation tells us that even a small amount of mass contains enormous energy. The C2 part, the speed of light squared, is a huge number. 1 kilogram of mass, if converted entirely to energy, would release 90 quadrillion joules. That's roughly the energy released by 20 megatons of TNT. Nuclear reactions tap into this. When uranium atoms split, a tiny fraction of their mass converts to energy. This tiny fraction is enough to power cities or destroy them. stars shine through this process. Every second, the sun converts about 4 million tons of mass into energy. This energy radiates outward at the speed of light, eventually reaching Earth as the sunlight that makes life possible. But for our story, the most important consequence of EMC2 is what it says about acceleration. Part 3. The barrier becomes clear. Why you can't reach light speed. Here's the heart of why nothing with mass can reach the speed of light. As you accelerate, your energy increases. But according to special relativity, this energy doesn't just make you go faster, it also increases your mass. At everyday speeds, this effect is negligible. Accelerate a car from rest to highway speed, and its mass increases by an amount far too small to measure. But as you approach light speed, the effect becomes dramatic. At 50% the speed of light, your mass has increased by about 15%. At 86% the speed of light, your mass has doubled. At 99% the speed of light, your mass is 7 times your resting mass. At 99.9% the speed of light, your mass is 22 times your resting mass. The pattern is clear. The closer you get to light speed, the more massive you become. And the more massive you are, the more energy you need to accelerate even a tiny bit faster. The mathematical relationship is precise. As your speed approaches light speed, your mass approaches infinity. To actually reach light speed would require infinite mass, which would require infinite energy. The universe doesn't contain infinite energy. Therefore, nothing with mass can reach light speed. This isn't a technological limitation. It's not that we haven't built a powerful enough engine yet. It's that the universe's mathematical structure makes it impossible. Particle accelerators confirm the limit. We've tested this extensively. Particle accelerators like the Large Hadron Collider routinely accelerate protons to 99.9999991% the speed of light. These protons carry enormous amounts of kinetic energy. Each one has roughly the same energy as a flying mosquito, which might not sound like much until you remember that a mosquito is trillions of times more massive than a proton. Yet despite having these enormous energies, the protons never exceed light speed, not even close. As they gain more energy, they don't go faster. They become more massive, exactly as Einstein predicted. This is one of the most precisely tested predictions in all of physics. Thousands of experiments over decades have confirmed it without exception. The cosmic speed limit is real. Why light travels at the cosmic speed limit? Here's something that might surprise you. The cosmic speed limit isn't really about light at all. Light just happens to travel at this speed because photons have no mass. Anything with zero mass automatically travels at this maximum speed. Photons do. Gravitational waves do. Gluons, the particles that carry the strong nuclear force, do. The cosmic speed limit is more fundamental than light. It's the maximum speed at which information can propagate through space. It's the speed of causality itself. This distinction is important. When we talk about nothing exceeding the speed of light, what we really mean is that nothing can exceed the maximum speed of causality. Light just happens to be the most familiar thing that travels at this speed. Part 4. What the speed limit means. Space and time are connected. Einstein's great insight was recognizing that space and time aren't separate entities. They're aspects of a four-dimensional fabric called spacetime. When you sit still, you're not motionless. You're moving through time at 1 second per second. This motion through time is as real as motion through space. When you start moving through space, something remarkable happens. Your motion through time slows down. The faster you move through space, the slower you move through time. Your total speed through space-time always equals the speed of light. That's the cosmic speed limit. You're always moving at light speed through space-time. The question is how that motion is divided between spatial dimensions and the time dimension. When you're sitting still, all your motion is through time. As you move through space, you divert some of that motion from the time direction into spatial directions. The faster you move through space, the slower you move through time. This explains time dilation. It's not something mysterious happening to clocks. It's the natural consequence of how space-time works. Causality has a speed limit. The cosmic speed limit creates a fundamental structure in how causes and effects relate to each other. From where you are right now, space-time divides into 3 regions. Your past light cone contains all events that could have influenced your present. These are events far enough in the past and close enough in space that light from them could have reached you by now. Your future light cone contains all events that you could potentially influence. These are events far enough in the future and close enough in space that light from you could reach them. And then there's elsewhere. All the events that are too far away and too close in time for light to travel between you and them. These events cannot causally interact with your present moment. They're space-like separated from you. This structure is fundamental. It's not just a limitation on how fast we can send signals. It's a fundamental aspect of how reality works. Cause and effect propagate at the speed of light, not faster. What if you could go faster? Some people wonder, what if we found a way around this limit? What if we discovered a loophole that let us travel faster than light? The answer isn't just we can't. It's that the question doesn't quite make sense. Going faster than light isn't impossible in the way that building a perpetual motion machine is impossible. It's more like asking about the north side of the North Pole. The concept breaks down. Mighty. If you could travel faster than light, you would arrive at your destination before you left. Not in the sense of time travel in science fiction, where you deliberately journey into the past. Rather, the mathematics of space-time inevitably leads to this conclusion. Different observers moving at different speeds disagree about which events happen first. This disagreement is harmless as long as no signals travel faster than light. But if faster than light signals were possible, you could create situations where a signal arrives before it was sent, allowing for paradoxes. You could send a message to your past self. You could know about events before they occurred. The logical structure of cause and effect would break down. The universe seems to protect itself against such paradoxes by making faster than light travel impossible. The cosmic speed limit isn't just a speed limit. It's a causality limit. Part 5. Implications for our universe. The observable universe has a boundary. Because light travels at a finite speed, and the universe has a finite age, there's a limit to how far we can see. Light from very distant galaxies has been traveling toward us since shortly after the Big Bang. But even light that's been traveling for 13.8 billion years, the entire age of the universe, has only covered a finite distance. This creates a cosmic horizon. Beyond a certain distance, we simply cannot see, not because the view is blocked, but because light from those regions hasn't had time to reach us yet. The observable universe extends about 46 billion light-years in every direction. The discrepancy between 13.8 billion years and 46 billion light-years comes from cosmic expansion, which we'll discuss more in a moment. But the key point is this: the cosmic speed limit creates a boundary on what we can observe. There are regions of the universe that we cannot see, not because of any limitation in our telescopes, but because of the fundamental structure of spacetime itself. We see the past, not the present. When you look at the moon, you're seeing it as it was 1.3 seconds ago. That's how long light takes to travel from the moon to your eyes. The sun appears as it was 8 minutes and 20 seconds ago. If the sun suddenly vanished, you would continue to see it shining for over 8 minutes. The sky would darken, and simultaneously Earth would cease to orbit, as the gravitational influence also propagates at the speed of light. When you look at stars, you're seeing them as they were years or centuries ago. Sirius, the brightest star in the night sky, is 8.6 light-years away. The light you see tonight left that star in early 2017. Betelgeuse, the red supergiant in Orion's shoulder, is roughly 700 light-years away. You're seeing it as it appeared during the late medieval period. The Andromeda Galaxy, visible as a faint smudge in dark skies, is 2.5 million light-years distant. You're observing it as it existed when our ancestors were still mastering stone tools. The most distant galaxies we've observed appear as they were over 13 billion years ago, when the universe was less than 1 billion years old. This temporal displacement is fundamental. You cannot see the universe as it exists right now. You can only see where it was when the light left those distant objects. The present moment of distant regions is hidden behind the time it takes for light to reach us. Cosmic expansion complicates everything. Here's where things become even more interesting. The universe is expanding. Space itself is growing, carrying galaxies along with it. This expansion doesn't violate the cosmic speed limit. Galaxies aren't moving through space faster than light. Space itself is expanding, and distant galaxies are being carried along. The crucial distinction: nothing can move through space faster than light, but space itself can expand as fast as it wants. No cosmic speed limit applies to the expansion of space. This leads to something remarkable. There are galaxies moving away from us faster than light, not through space, but because the space between us and them is expanding so rapidly. Light from these galaxies is racing toward us at the speed of light through their local space. But space is expanding faster than the light can traverse it. The light is like a person running on a treadmill that's accelerating faster than they can run. They're running forward, but falling behind. This creates a cosmic event, horizon. Galaxies beyond a certain distance are receding so fast that their light will never reach us, ever. Even given infinite time, we will never see them. The universe is not just vast, Part of it is permanently beyond our reach, hidden not by distance alone, but by the combination of distance and expansion. We live in an island universe. Because of the cosmic speed limit and cosmic expansion, we're isolated. The observable universe is our island. Beyond it lie regions we cannot see, cannot reach, cannot communicate with. This isolation is fundamental and permanent. No technology, no matter how advanced, can overcome it. You cannot send a signal to a galaxy beyond the cosmic horizon. You cannot receive information from it. It might as well not exist, at least not in any way that can affect us. Future civilizations arising billions of years from now will inhabit an even more isolated cosmos. Accelerating cosmic expansion will have carried even more galaxies beyond their horizon. They will see fewer galaxies than we do. Eventually, only our local cluster of gravitationally bound galaxies will remain visible. These future observers will have almost no evidence that the universe was once full of galaxies. The cosmic speed limit, combined with expansion, will have hidden that truth from them. We're fortunate to live in an epoch when the universe reveals its structure clearly. The evidence is visible if we look for it, but this window is temporary. The cosmic speed limit ensures that. Part 6. Deeper into the structure. Spacetime is not what you think. Most people imagine space as a fixed stage where events occur, and time as a separate river flowing forward. Einstein showed this picture is wrong. Space and time are interwoven into a single geometric structure, spacetime. Events don't happen in space and time. They happen in spacetime, at specific locations in 4 dimensions, 3 spatial, 1 temporal. The cosmic speed limit emerges from the geometry of this 4-dimensional fabric. It's not a rule imposed from outside. It's built into the structure of spacetime itself, like how the interior angles of a triangle sum to 180 degrees on a flat surface. In spacetime, there's a quantity called the spacetime interval that remains the same for all observers regardless of their motion. This invariant interval is what allows different observers moving at different speeds to agree on the fundamental structure of events, even though they disagree on measurements of space and time separately. The cosmic speed limit falls out of this geometric structure. It's the ratio between how time is measured and how space is measured, a geometric constant built into spacetime itself. Light cones define reality. From any event in spacetime, you can draw light cones, surfaces representing where light could travel to or from that event. The future light cone contains all events that could potentially be reached by a signal starting from the event. The past light cone contains all events that could have sent a signal to reach the event. These light cones divide spacetime into causal regions. Events inside your past light cone could have influenced you. Events inside your future light cone you could potentially influence. Events outside both light cones are causally disconnected from you. This structure is absolute. All observers agree on it, regardless of their relative motion. You might disagree with another observer about which events happen simultaneously, but you'll both agree on which events can causally influence which other events. The cosmic speed limit creates this causal structure. It's not just a maximum speed for physical objects. It's the defining feature of how reality is organized. Why does this structure exist? Physicists have wondered whether the cosmic speed limit is arbitrary. Could the universe have been different? Could the speed of light have been faster or slower? The answer is subtle. The numerical value, 289,792, 458 meters per second, is arbitrary. It depends on human choices about how to define meters and seconds. But the existence of some maximum speed for causality seems fundamental. A universe without a cosmic speed limit would be very different, perhaps impossibly different. Without a maximum speed for causal influences, there would be no clear separation between past, present, and future. Cause and effect could propagate instantaneously across any distance. The entire universe would be entangled in immediate causal relationships. Such a universe might not allow for stable structures, local causation, or the kind of protected regions where complexity can evolve. Life and consciousness might require a universe with a cosmic speed limit. We don't fully understand why space-time has the structure it does, but we can observe that this structure, with its built-in cosmic speed limit, creates the conditions for everything we know to exist. Part 7. Testing the limit. Extreme physics confirms Einstein. The cosmic speed limit has been tested in countless ways, under extreme conditions, and it has never failed. Particle colliders accelerate particles to within tiny fractions of light speed. The Large Hadron Collider accelerates protons to 99.91% of light speed. At these speeds, the particles are moving only 3 meters per second slower than light itself. These protons have been given enormous amounts of energy, yet they don't go faster. They become more massive, exactly as relativity predicts. The equations that Einstein wrote down in 1905 describe their behavior perfectly. Cosmic ray particles provide even more extreme tests. These are particles created in violent cosmic events, supernova explosions, matter falling into black holes. Some have energies millions of times greater than anything we can produce in our colliders. Yet even these ultra-high energy particles never exceed light speed. They obey the cosmic speed limit perfectly. GPS proves it daily. Every time you use GPS, you're relying on the cosmic speed limit and its consequences. GPS satellites orbit Earth at about 14,000 kilometers per hour. At this speed, time dilation causes their clocks to run slower than clocks on the Earth's surface by about 7 microseconds per day. But the satellites also orbit at high altitude, where gravity is weaker. General relativity tells us that time runs faster in weaker gravity. This effect causes the satellite clocks to run faster than Earth clocks by about 45 microseconds per day. The net effect: satellite clocks gain about 38 microseconds per day compared to Earth clocks. This sounds tiny, but GPS works by precisely timing signals traveling at the speed of light. Light travels 30 centimeters in 1 nanosecond. In 38 microseconds, light travels 11 kilometers. If GPS didn't correct for these relativistic effects, your position would be wrong by about 11 kilometers per day. The errors would accumulate. Within a week, GPS would be useless. The fact that GPS works proves that Einstein's predictions about time dilation and the cosmic speed limit are correct. Gravitational waves move at light speed. In 2015, the LIGO detectors made the first direct observation of gravitational waves, ripples in spacetime itself, created when two black holes collided 1.3 billion light-years away. These waves traveled across the universe for 1.3 billion years before reaching Earth. When they arrived, LIGO measured their speed. Gravitational waves travel at exactly the speed of light, not approximately, exactly, time twos. This makes sense in Einstein's framework. Gravity isn't a force in the traditional sense. It's the curvature of space-time. Gravitational waves are ripples in this curvature, propagating through space. Like all information in our universe, these ripples travel at the cosmic speed limit. The precision measurement of gravitational wave speed provided yet another confirmation that the speed of light isn't just a property of light. It's a fundamental property of space-time itself. Part 8. What it means for us. We are built from light-speed interactions. Every atom in your body is held together by electromagnetic forces. These forces are mediated by photons, particles of light, which travel at the speed of light. When electrons orbit atomic nuclei, when chemical bonds form between atoms, when molecules twist and fold into the shapes that make them functional, all of these processes occur through electromagnetic interactions propagating at light speed. You exist because of countless light-speed interactions happening continuously throughout your body. Your atoms, your molecules, your cells, all held together by forces that respect the cosmic speed limit. Even the strong nuclear force, which binds quarks together inside protons and neutrons, propagates at light speed. It's mediated by gluons, massless particles that travel at the cosmic speed limit. Everything about you, from your smallest components to your largest structures, is shaped by this fundamental constant. Your perception is delayed. When you look at your hand, you're not seeing it as it exists right now. You're seeing it as it was nanoseconds ago, the time it took light to travel from your hand to your eyes. This delay is tiny for nearby objects, but it's real. And for distant objects, the delay becomes significant. When you watch a sunset, you're seeing the sun as it was 8 minutes ago. The sun has moved slightly in that time. The image you see is where the sun was, not where it is now. Every perception you have of the external world arrives after a delay determined by the cosmic speed limit. You never perceive the present moment of distant objects. You always perceive their past. Even your perception of your own body is delayed. The nerve signals that carry information from your extremities to your brain travel at speeds far slower than light, roughly 100 meters per second for the fastest nerve fibers. Your brain's perception of your toe is delayed by about 20 milliseconds compared to your brain's perception of your face. You live in a reconstructed present, a synthesis your brain creates from information arriving at different times, from different distances, through different mechanisms. The cosmic speed limit shapes even your subjective experience of reality. Communication across space is fundamentally limited. The cosmic speed limit creates fundamental constraints on communication. A message sent from Earth to Mars takes between 3 and 22 minutes to arrive, depending on orbital positions. A conversation with someone on Mars involves delays of 6 to 44 minutes between question and answer. For the outer planets, the delays grow longer. A message to Saturn takes over an hour each way. To Voyager 1, currently at the edge of the solar system, a signal takes over 22 hours to arrive. These aren't technological limitations. We could build more powerful transmitters and more sensitive receivers, but we cannot make signals travel faster than light. The delays are fundamental. For interstellar distances, the delays become generational. A message to the nearest star system takes 4.3 years to arrive. A reply takes another 4.3 years to return. Nearly 9 years for a single exchange. To more distant stars, the delays stretch into decades, centuries, millennia. Communication across these distances isn't really communication in any meaningful sense. It's more like leaving messages for distant future recipients. Time capsules launched into space. The cosmic speed limit ensures that beings separated by large distances cannot have conversations, cannot coordinate in real time, cannot maintain the kind of immediate connection we take for granted with people in the same room. Part 9. Philosophical implications. The structure of causality. The cosmic speed limit creates a clear structure for cause and effect. Causes precede effects, separated by time sufficient for light to travel between them. This structure seems essential for the universe to make sense. Without it, effects could precede causes. Information could propagate instantaneously, making the entire universe a tangled web of instant causation with no clear direction to time. Some philosophers argue that the cosmic speed limit is necessary for free will and meaningful choice. If influences could propagate instantly, your decisions now would be immediately affected by events anywhere in the universe. There would be no protected space where local causation could operate. But with a cosmic speed limit, you exist in a bubble where local causation dominates. Events in distant galaxies can't affect you until sufficient time has passed for light to travel between you and them. Your choices unfold according to local conditions, local laws, local causes. Whether or not you accept this argument for free will, the cosmic speed limit clearly creates a particular structure for how reality unfolds, a structure with local regions separated by distances that information must traverse at a finite speed. The present moment becomes relative. One of the strangest consequences of special relativity is that observers moving at different speeds disagree about which events happen simultaneously. Imagine two events occurring in distant locations, say a supernova exploding in one galaxy and a star forming in another. These events are so far apart that light from one cannot reach the other quickly. For an observer at rest relative to these events, they happen simultaneously at exactly the same time. But for an observer moving at high speed, one event happens before the other. A different observer moving in a different direction might see them occur in the opposite order. All three observers are correct. There's no absolute fact about which event happens first. The order depends on the observer's motion. This seems to violate our deepest intuitions about time. Surely there's a fact about which events happen first. Surely the universe has a single timeline where events occur in a definite sequence. But special relativity says no. For events far enough apart and close enough together in time, there's no observer-independent fact about their ordering. The concept of now across vast distances doesn't exist in any absolute sense. The cosmic speed limit creates this relativity of simultaneity. It's part of what it means for spacetime to have the structure it does. Time times 2s. Are we alone because of the speed limit? The Fermi paradox asks, where is everybody? If intelligent life is common in the universe, why haven't we detected any signs of it? Many proposed solutions focus on biology, technology, or sociology. Maybe life is rare. Maybe intelligence rarely evolves. Maybe civilizations inevitably destroy themselves. But maybe the answer is simpler. Maybe the cosmic speed limit keeps civilizations isolated. Even if the galaxy teems with intelligent species, each develops in isolation, surrounded by vast distances that light takes years or centuries to cross. Communication is prohibitively slow. Travel is effectively impossible. Colonization would require generation ships. Societies unto themselves, cut off from their origin worlds. The cosmic speed limit might fragment the galaxy into countless isolated civilizations, each exploring their local neighborhood, each unaware of neighbors beyond the reach of patient, multi-generational communication efforts. We might not be alone. We might simply be isolated, separated from our cosmic neighbors by distances too vast, and a cosmic speed limit too constraining for meaningful contact. Part 10. The deeper questions. Why this speed? Why is the cosmic speed limit exactly 299,792,458 meters per second? Why not faster? Why not slower? The answer is both simple and profound. The numerical value is arbitrary. It's a result of human choices about how to define meters and seconds. We could redefine these units to make the speed of light any number we wanted. What's fundamental isn't the numerical value. It's that a cosmic speed limit exists at all, and that electromagnetic radiation travels at this limit. But we can still ask, why this ratio between spatial distances and temporal durations? Why is light speed fast enough for chemistry to work, but slow enough for stable matter to exist? If light speed were much slower, chemistry would be different. The fine structure constant, which governs how strongly matter interacts with light, would change. Atoms might not be stable. The universe might be very different. If light speed were much faster, causality would have different properties. The past light cone of any event would encompass more of space-time. The separation between causally connected and causally disconnected events would change. We don't know why the speed of light has the value it does relative to other fundamental constants. But we observe that it creates a universe where atoms are stable, chemistry is possible, and structures like stars, planets, and living organisms can form. Perhaps the cosmic speed limit is part of what allows a universe to be comprehensible at all. Is the speed of light truly constant? Some physicists have speculated that the speed of light might not be truly constant. Perhaps it changes over cosmic time. Perhaps it varies with location. Perhaps it depends on the energy of the light. These ideas remain speculative. Every measurement confirms that the speed of light is constant across time and space. Light from distant galaxies, traveling for billions of years, arrives with properties consistent with a constant light speed throughout its journey. High-energy photons and low-energy photons from the same source arrive at the same time, despite having traveled for millions of years. This wouldn't happen if light speed depended on photon energy. The cosmic microwave background, the oldest light in the universe, has properties consistent with light traveling at constant speed for 13.8 billion years. If the speed of light changed, we would see signatures of that change in the universe's structure and history. We don't see such signatures. The cosmic speed limit appears to be truly constant, a fixed feature of spacetime's geometry, unchanging across all of space and time. Could we ever get around it? Science fiction often features faster-than-light travel, warp drives, hyperspace, wormholes, fictional technologies that circumvent the cosmic speed limit. Could any of these work? Could we find a loophole? Wormholes are mathematically possible in Einstein's general relativity. They're solutions to the equations, tunnels through space-time connecting distant regions. In principle, you could enter a wormhole and emerge light years away without traveling faster than light locally. You'd be taking a shortcut through the geometry of space itself. But there are problems. First, we've never observed a wormhole. We don't know if they exist. Second, the equations suggest that keeping a wormhole open requires exotic matter with negative mass, something we've never detected and which might not exist. Third, even if wormholes exist and can be stabilized, using one for travel might create time paradoxes that the laws of physics prevent. Warp drives face similar issues. The Alcubierre drive, a theoretical concept proposed by physicist Miguel Alcubierre, would compress space in front of a ship and expand it behind, creating a wave of space-time that carries the ship faster than light. But it also requires exotic matter with negative energy, and it might create regions of infinite energy density that would destroy the ship. Every loophole we've imagined faces fundamental obstacles. The universe seems to protect its cosmic speed limit through multiple mechanisms. Most physicists believe that faster-than-light travel is impossible, not just technologically, but fundamentally. The cosmic speed limit isn't a challenge to be overcome. It's a basic feature of reality. Part 11. Living with the limit. The universe is patient. The cosmic speed limit makes the universe vast in a particular way. Not just large in space, but large in time. Distances translate directly to durations. A light year isn't just a measure of space. It's a measure of time, the time light takes to travel that distance. When we say a star is 100 light years away, we're saying it takes light 100 years to travel from that star to us. This gives the universe a particular pace. Events unfold slowly across cosmic distances. Signals take years to propagate. Changes in distant regions don't affect us until sufficient time has passed. The universe isn't rushed. It operates on timescales long compared to human lifetimes, but appropriate for its own vast distances. We are connected to the cosmos. Despite the isolation imposed by the cosmic speed limit, we remain connected to the broader universe. The atoms in your body were forged in the cores of stars that exploded billions of years ago. The heavy elements, carbon, nitrogen, oxygen, everything beyond hydrogen and helium, were created in stellar furnaces and scattered into space by supernovae. These atoms traveled through space for eons, eventually condensing into the molecular cloud that formed our solar system. They assembled into planets, then into living organisms, then into you. You are made of star material. The cosmic speed limit governed every step of this process. The light from those ancient stars traveled at light speed. The shock waves from their explosions propagated at a significant fraction of light speed. The atoms they released drifted through space at speeds far slower than light, eventually reaching the location where Earth would form. Every atom in your body has a cosmic history, connected to distant places and ancient times through processes that respect the cosmic speed limit. Our future is local. Because of the cosmic speed limit, humanity's future, at least for the foreseeable future, is local. We might someday travel to nearby stars. The nearest star system, Alpha Centauri, is 4.3 light-years away. With current technology, a journey there would take tens of thousands of years. With more advanced propulsion, perhaps centuries. With hypothetical near-light-speed propulsion, perhaps decades. These are long timescales, but not impossibly long. Humanity could potentially reach nearby stars given sufficient will and resources. But more distant stars, other galaxies, these seem forever beyond reach. The cosmic speed limit makes interstellar distances vast and galactic distances incomprehensible. We are creatures of our local cosmic neighborhood. Our future likely lies here, in our solar system, perhaps extending to nearby stars, but ultimately confined to a small region of the galaxy by the fundamental physics of spacetime. This isn't cause for despair. Our local neighborhood is vast by human standards. The solar system alone contains resources sufficient for billions of years of civilization. Thousands of nearby stars offer potential destinations for exploration and settlement. We may be isolated on cosmic scales, but we're not confined. Our local universe offers endless possibilities for growth, exploration, and discovery. Part 12. The meaning of the limit. A universe of order. The cosmic speed limit represents a deep kind of order in the universe. Despite all the complexity, all the chaos, all the unpredictability of events, this fundamental constant remains unchanged. Wherever you are in the universe, whatever you're made of, however fast you're moving, the speed of light is the same. This constancy is remarkable. It means the universe has regularities that transcend local conditions. It means physical laws are universal. It means we can learn about distant regions by studying local physics. This universality makes science possible. If physical laws changed from place to place or time to time, we couldn't generalize from local experiments to cosmic predictions. The fact that the cosmic speed limit is truly constant everywhere and always means the universe follows comprehensible rules. Time, Chantus, a universe of limits. The cosmic speed limit reminds us that the universe has boundaries. Not all things are possible. Not all speeds can be achieved. Not all distances can be traversed in arbitrary time. These limits aren't failures of human ingenuity. They're features of reality itself. Understanding limits is part of understanding the universe. In a strange way, limits make things interesting. An infinite universe without structure, without boundaries, without constraints would be formless and meaningless. The specific limits that govern our universe, including the cosmic speed limit, create the structure that makes complex phenomena possible. Stars shine because nuclear fusion has particular rates and energies. Atoms are stable because electromagnetic forces have particular strengths. Life exists because chemistry works in particular ways. All of these depend on the fundamental constants, including the speed of light, having the values they do. The limits aren't obstacles preventing a better universe. They're features creating the only universe we could inhabit. A universe we're part of. You're not separate from these cosmic principles. You're an expression of them. The speed of light governs how neurons fire in your brain. It governs how proteins fold in your cells. It governs how photosynthesis captures energy from sunlight to power the biosphere. Every thought you think emerges from electrical and chemical processes mediated by forces propagating at light speed. Every sensation you experience arrives after light speed delays. Every action you take propagates into the world through interactions respecting the cosmic speed limit. You are built from and sustained by processes that obey this fundamental constant. It's not something external to you. It's woven into your very being. The speed limit as gift. Perhaps the cosmic speed limit isn't a restriction, but a gift. It creates space for local causation, for complexity to evolve, for meaningful choices to exist. It protects us from instant cosmic scale chaos. Events in distant galaxies can't immediately disrupt local processes. We have time to adapt, to respond, to build structures that persist. It creates the pace of cosmic evolution. Stars burn for billions of years because fusion proceeds at rates governed by fundamental constants, including light speed. Galaxies evolve over eons, giving time for complexity to emerge. Without the cosmic speed limit, the universe might be a blur of instant causation, with no clear direction to time, no stability, no possibility for the patient processes that led to stars, planets, and life. The limitation creates the possibility. The boundary defines the space within which we exist. Closing, the constant in the cosmos. We began this journey by noting a number, 299,792, 458 meters per second, the speed of light, the cosmic speed limit, the maximum rate at which causality propagates through space. We've seen how this number emerges from the deep structure of space-time itself, how it's not really about light but about the geometry of reality, how it shapes everything from the behavior of subatomic particles to the evolution of the entire universe. We've seen how this limit has been measured, tested, and confirmed in countless ways, how it governs our daily lives through technologies like GPS, how it determines what we can see of the universe and how we see it, always looking into the past, never perceiving the distant present. We've explored how this limit creates isolation across cosmic distances, making the universe vast not just in space but in time, how it shapes causality, restricts communication, and defines which regions of space-time can interact. And we've reflected on what this means for us. Beings made of atoms held together by light-speed forces, perceiving a universe through light-speed signals, living in a cosmos whose structure is defined by this fundamental constant. The cosmic speed limit is neither enemy nor ally. It simply is, a basic feature of reality, as fundamental as the existence of space and time themselves. In understanding it, we understand something deep about the universe we inhabit. We see that reality has a particular structure, governed by comprehensible laws, creating the conditions for everything we know. Nothing can go faster than the speed of light. This isn't a limitation imposed from outside, but a truth woven into the fabric of space-time. And in recognizing this truth, we glimpse the profound order underlying the cosmos. As you drift towards sleep tonight, consider this. Every photon that has ever existed, from the first light after the Big Bang to the gentle glow of your bedroom lamp, has traveled at exactly the same speed, 299,792, 458 meters per second, no faster, no slower, perfectly constant across all of space and time. This constancy connects you to the cosmos in ways both subtle and profound. The light entering your eyes carries information at this cosmic speed. The forces holding your atoms together propagate at this speed. The structure of space-time that makes your existence possible is defined by this speed. You are part of a universe governed by this fundamental limit, a universe of order, a universe of structure, a universe where nothing, absolutely nothing, can go faster than the speed of light. And in that unchanging constant, in that universal limit, there is something beautiful, something that speaks to the deep order underlying all of reality. Rest well, knowing you live in a cosmos where the laws of physics are the same everywhere, for everyone, at all times. Where the speed of light connects you to everything that has ever been and everything that will ever be.